How long would it actually take for a spacecraft to leave our solar system? It's a question that feels both thrilling and humbling at the same time, because the answer pushes the limits of what we know about space, technology, and time itself. Even with the fastest machines humanity has ever built, the distances involved are so enormous that they stretch our imagination to its breaking point. To put it simply, our solar system isn't a neat boundary with an exit sign. It's a vast, invisible empire ruled by the sun's gravity and energy, extending trillions of kilometers into the void. And if you want to find out exactly how long it would really take, watch this video till the end and subscribe to the channel. Let's begin. When we talk about leaving the solar system, most people instinctively picture a spacecraft passing the orbit of Pluto, that lonely, icy world on the edge of our planetary family. But in scientific terms, crossing Pluto's path isn't truly the end of the sun's domain. Our solar system doesn't stop where the planets end. It extends far, far beyond. What really defines the boundary of our solar system is something called the heliopause. This is the invisible frontier where the sun's influence finally gives way to the vastness of interstellar space, a place where the solar wind, a continuous stream of charged particles blowing outward from the sun, no longer has the power to push against the thin, interstellar gas that fills the galaxy. Inside this enormous bubble, known as the heliosphere, the sun's magnetic field and solar wind dominate, shaping an enormous protective cocoon that shields the planets from much of the cosmic radiation beyond. Think of it as the sun's personal bubble in space, expanding, shifting, and breathing with the rhythm of solar activity. But at a certain point, roughly 120 to 150 astronomical units from the sun, that's about 18 to 23 billion kilometers, this bubble loses its strength. The solar wind slows, weakens, and eventually is overpowered by the pressure of particles and magnetic fields coming from other stars. That transition zone, the point where the solar wind can go no farther, is the heliopause. Crossing the heliopause means more than traveling to a new place. It means stepping into an entirely new environment. Beyond it lies interstellar space, a region no longer governed by our sun's magnetic influence. Here, the faint whispers of other stars begin to shape the surrounding medium. The particles, fields, and radiation here aren't from our solar system at all. They belong to the galaxy itself. So when scientists say a spacecraft has left the solar system, they mean it has crossed this threshold, entering a place where the sun's protective bubble ends and the true interstellar sea begins. This boundary isn't a hard wall either. It shifts with the solar cycle, swelling outward when the sun's activity is strong and contracting slightly during quieter periods. That means the exact distance of the heliopause isn't fixed. It's alive, fluctuating, almost breathing. Only 2 spacecraft have ever crossed it, and their data revealed just how mysterious and dynamic this region is. To leave the solar system, then, is to go beyond the reach of the sun's breath, beyond the invisible line that marks the end of our star's dominion and the beginning of everything else. To truly grasp what it means to leave the solar system, you first have to understand just how impossibly large it is. Our human senses, and even our everyday sense of far away, simply aren't built for these kinds of distances. Space isn't just big, it's mind-bendingly vast. When astronomers talk about billions of kilometers or astronomical units, the numbers quickly lose all meaning. So let's scale it down to something we can picture. Imagine the sun as a basketball sitting in the middle of a large park. On that same scale, Earth would be no bigger than a tiny peppercorn, about 25 meters away, roughly the distance of a swimming pool. Mercury and Venus would be marbles tucked closer to the sun, while Mars would be another peppercorn, a bit farther out. Now, to reach Jupiter, the gas giant we think of as a neighboring planet. You'd have to walk almost 3 football fields away. Saturn would be about twice that distance. Uranus and Neptune? You'd have to travel nearly 1 kilometer from the basketball to find them. And what about Pluto, the little icy wanderer that once marked the edge of our planetary family? On this same scale, Pluto would orbit nearly 1.2 kilometers away. At that point, you'd probably feel like you've reached the end of the solar system, but you haven't even come close. The edge, the true outer boundary, the heliopause, would be several kilometers farther still, maybe 5 to 7 kilometers from that basketball sun, depending on solar activity. And beyond that, stretching thousands of kilometers further on this same scale, lies the mysterious Oort cloud, a vast shell of icy bodies that marks the outermost whispers of the sun's gravitational influence. So when you hear that Voyager 1 has traveled more than 24 billion kilometers from Earth, that number represents only a tiny step in a cosmic marathon. The planets we know and love occupy only a minuscule fraction of the solar system's true size. The rest, a vast gulf of darkness filled with drifting dust, radiation, and the slow fade of the sun's magnetic breath, stretches on and on, so far that even light, traveling at 300,000 kilometers per second, would take more than a day to cross it. In this sense, our solar system isn't a compact family of planets orbiting neatly around the sun. It's an empire of unimaginable reach, a sprawling sphere of influence that extends deep into interstellar space. When we think of a spacecraft leaving it, we're not talking about crossing a fence or passing a distant planet. We're talking about venturing beyond the borders of a star's very power. As we drift farther outward from our imagined solar system scale, past Neptune's frozen orbit and even beyond Pluto's lonely path, we approach a region that marks one of the greatest frontiers in human exploration, the heliopause. This mysterious boundary is not something we can see, and it doesn't announce itself with a signpost or a sudden change in scenery. It is instead an invisible yet profoundly significant transition, the point where the sun's protective bubble, called the heliosphere, finally gives way to the cold interstellar space that exists between the stars. To understand what the heliopause truly is, we first have to picture the heliosphere itself. Think of the sun as not just a source of light and heat, but as a kind of cosmic engine constantly blowing out a stream of charged particles, the solar wind. This wind rushes outward in every direction at hundreds of kilometers per second, carrying with it the sun's magnetic field and forming a vast, teardrop-shaped bubble that surrounds everything in our solar system. Within this bubble, every planet, asteroid, and comet is bathed in the influence of our star's magnetic reach. It's the sun's invisible territory, and it stretches far beyond anything we can imagine, over 100 times farther from the sun than the Earth is. However, the solar wind doesn't go on forever. Eventually, it collides with the thin gas, dust, and magnetic fields that fill the space between stars, what astronomers call the interstellar medium. When that happens, the solar wind begins to slow down, like ocean waves meeting the resistance of the shore. There's a region where it starts to decelerate sharply, known as the termination shock, followed by a turbulent zone where solar and interstellar particles intermingle. And beyond that chaotic region lies the heliopause, the ultimate edge of the sun's influence, where the outward pressure of the solar wind is perfectly balanced by the inward pressure of the interstellar medium. It's the boundary that separates ours from everything else. Crossing this line isn't just symbolic, it's a scientific milestone. Inside the heliosphere, charged particles from the sun dominate the environment, shaping the radiation levels, magnetic fields, and particle flows a spacecraft encounters. Beyond the heliopause, however, the density, direction, and energy of those particles change dramatically. Spacecraft instruments detect far more high-energy cosmic rays from the galaxy, and the magnetic field they measure no longer aligns with the Sun's. In other words, the spacecraft enters interstellar space, a completely new environment that no probe or human-made object had ever experienced before the 21st century. So far, only 2 spacecraft have ever reached this boundary, Voyager 1 and Voyager 2. These twin explorers were launched by NASA in 1977, originally intended to study the outer planets. But thanks to clever engineering, careful trajectory planning, and a bit of cosmic luck, they became humanity's first emissaries to the stars. Voyager 1 crossed the heliopause on August 25, 2012, at a distance of about 121 astronomical units from the Sun, roughly 18 billion kilometers. Voyager 2 followed 6 years later, in November 2018, crossing at about 119 astronomical units. The data they sent back astonished scientists. When Voyager 1 first crossed the heliopause, its instruments recorded a sharp drop in solar particles and a simultaneous surge in high-energy cosmic rays, a clear sign it had entered interstellar space. Yet, in many ways, it was still tethered to the Sun, moving through a region that was influenced by the solar magnetic field but no longer controlled by it. Voyager 2's data later confirmed that the heliopause isn't uniform. It's irregular, rippled, and shaped by solar activity cycles, like the shifting edge of a giant balloon that expands and contracts with the Sun's moods. The discoveries made at this boundary are extraordinary. They've revealed that the heliopause acts as a shield, filtering much of the cosmic radiation that would otherwise bombard our solar system. It's our Sun's invisible armor against the harsh environment of the galaxy. Without it, the planets, including Earth, would face far higher levels of cosmic radiation, potentially affecting atmospheres, biological evolution, and even the delicate balance of climate. The fact that we've now sent 2 tiny probes through this cosmic frontier is one of humanity's quietest yet most profound achievements. And perhaps what's most fascinating is just how far those voyages still are from being truly gone. Even after crossing the heliopause, they remain under the Sun's gravitational influence. In a way, they're still part of our solar system's story, still circling ever so slightly around our star, though at distances so great it would take light over 20 hours just to reach them. These spacecraft, now drifting silently in the deep, continue to send faint signals home, whispering across billions of kilometers, telling us what it feels like to be beyond the Sun's reach. The heliopause, then, isn't just a scientific concept. It's a threshold of identity, the line where home ends and the galaxy begins. And for the first time in history, we've crossed it. We've touched the edge of our Sun's kingdom and stepped into the interstellar sea. Yet this achievement, as monumental as it is, only opens more questions. How far do we need to travel before we escape the Sun's gravitational grip entirely? How long would it take to reach another star? And what does leaving even mean when the Sun's pull extends light years into space? These questions lead us naturally to the next part of our journey, the story of the Voyager spacecraft themselves, the pioneers who carried us beyond the heliopause and showed us what lies at the true edge of the solar system. In the summer of 1977, at a time when the world was still marveling at color televisions and personal computers were barely a novelty, humanity did something extraordinary. We launched 2 robotic emissaries toward the unknown. Among them was Voyager 1, a spacecraft destined to become the farthest human-made object from Earth, a title it still holds to this day. Its story is not just about technology and science, but about ambition, the bold desire of our species to reach beyond the limits of what we can see, to explore realms that had only existed in the imagination. Voyager 1's journey began on September 5th, 1977, just 16 days after its twin, Voyager 2, took off from Cape Canaveral, Florida. Both spacecraft were part of NASA's Voyager program, an ambitious mission designed to take advantage of a rare celestial alignment that occurs only once every 176 years. This alignment of the outer planets, Jupiter, Saturn, Uranus, and Neptune, offered a unique opportunity. By using the gravity of each planet to slingshot the spacecraft onward, NASA could send a probe farther and faster than ever before, while conserving precious fuel. The plan was ingenious, a delicate dance of physics and timing that would turn planetary motion itself into a propulsion system. Voyager 1's primary mission was to explore Jupiter and Saturn, two worlds that, at the time, were little more than fuzzy orbs in telescopes. Scientists hoped to study their atmospheres, moons, and magnetic fields, and to send back images that could transform our understanding of the outer solar system. And transform it they did. When Voyager 1 reached Jupiter in 1979, it revealed a world of staggering dynamism, a planet alive with swirling storms, auroras, and volcanic activity on its moons. Its cameras captured the first close-up images of Jupiter's Great Red Spot, a colossal storm large enough to swallow 3 Earths, and sent back astonishing footage of Io, Jupiter's moon, erupting with molten lava. It was the first time humanity had witnessed active volcanoes beyond Earth. A year later, in 1980, Voyager 1 made its historic flyby of Saturn, giving us our first detailed look at the planet's iconic rings and its moon Titan. Titan's thick orange haze intrigued scientists immediately. It appeared to have a dense atmosphere rich in organic compounds, perhaps similar to the conditions on early Earth. Voyager's instruments couldn't see through Titan's smog, but they confirmed it was the only moon in the solar system with an atmosphere dense enough to sustain weather patterns. This single discovery alone justified the mission's cost many times over. After completing its flyby of Saturn, Voyager 1's path diverged from that of its twin. Rather than continuing outward along the plane of the planets, it was sent on a steep trajectory northward out of the ecliptic, the flat, disk-like region where most planets orbit. This path would take it away from the rest of the solar system, toward the outer boundaries of the Sun's influence. While its primary planetary mission was over, Voyager 1 had begun its secondary and far more historic mission to explore the outermost frontier, the edge of the solar system itself. What makes Voyager 1 remarkable is not just where it went, but how long it has lasted. The spacecraft was built in an era before digital computers were commonplace. Its memory, a mere 68 kilobytes, is smaller than that of a basic photo on your smartphone today. It communicates using an antenna no more powerful than a car's headlight bulb, yet it sends signals across billions of kilometers that take over 20 hours to reach Earth. Its power comes from 3 nuclear batteries, radioisotope thermoelectric generators, which convert the heat of decaying plutonium into electricity. Even after nearly half a century, those batteries continue to power a few of its key instruments, allowing it to send data from the edge of interstellar space. But Voyager 1 carries more than scientific instruments. On its side is a gold-plated record, a golden record, containing sounds and images meant to represent the diversity of life and culture on Earth. It includes greetings in 55 languages, music from around the world, sounds of nature, and even a message from then US President Jimmy Carter. The record, along with a diagram showing how to find our planet, was designed as a time capsule, a message to any potential extraterrestrial intelligence that might someday encounter the spacecraft. It is a profoundly human gesture, a small artifact of who we were cast into the cosmic ocean. As Voyager 1 traveled farther, it broke record after record. By 1990, it was so distant that NASA decided to turn its camera back toward home capturing one of the most famous images in history, the pale blue dot. From 6 billion kilometers away, Earth appeared as a faint speck of light suspended in a sunbeam. Carl Sagan, who had championed the idea of taking that picture, later wrote words that became immortal. "Look again at that dot. That's here. That's home. That's us." In that moment, Voyager 1 transformed from a machine of exploration into a mirror for our species, a reminder of our smallness, our unity, and our capacity for wonder. Decades later, Voyager 1 would continue its outward journey, crossing into interstellar space in 2012. Even now, it remains in contact with Earth, sending faint data packets through NASA's Deep Space Network, a constellation of massive radio antennas scattered across the globe. Its signal is unimaginably weak, a whisper across the void, but still detectable. Every bit of information it transmits expands our understanding of what lies beyond the Sun's protective reach. Today, Voyager 1 is over 24 billion kilometers from home, more than 160 times the distance between Earth and the Sun. It's traveling at about 17 kilometers per second, hurtling through interstellar space toward the constellation Ophiuchus. In another 300 years, it will reach the outer edge of the Oort cloud, the distant shell of icy bodies that marks the Sun's gravitational frontier. And though its instruments will long be silent by then, its journey will continue for billions of years, silently drifting among the stars. Voyager 1's launch was not just a technical triumph, it was a philosophical one. It marked the moment when humanity decided that curiosity would not be limited by distance, time, or lifespan. It carries our curiosity, our science, our art, and our hope, moving ever farther into the dark, carrying a message from one small world to the rest of the galaxy. And as it drifts farther into interstellar space, its legacy lights the way for all future explorers who will someday follow. Voyager 1's journey from its 1977 launch to the edge of the heliosphere is one of the most extraordinary odysseys in human history, a voyage not just of distance, but of time. Over the span of 35 years, this small spacecraft traveled farther than any object we've ever built, moving steadily outward through the great expanse of the Sun's influence until, in 2012, it finally crossed into the interstellar sea. Its path is the perfect illustration of patience in exploration, slow, steady, and relentless, carrying humanity's ambition across the most distant frontier ever reached. When Voyager 1 left Earth in September 1977, it was already moving faster than anything built before it. Within months, it had reached the asteroid belt, and by early 1979, it was closing in on Jupiter, the first major waypoint in its mission. There, it used Jupiter's immense gravity to slingshot itself towards Saturn, accelerating to over 17 kilometers per second relative to the Sun. This gravity assist was one of the great engineering and navigational feats of the space age, a precise maneuver that traded orbital energy for speed. Without it, Voyager 1 would never have reached the outer solar system in a human lifetime. After the spectacular encounters with Jupiter and Saturn, Voyager 1's primary mission was complete by late 1980. Its cameras were powered down to conserve energy, but its journey had only just begun. From that point on, it became an explorer of the outer heliosphere, the vast, turbulent region where the solar wind gradually weakens as it pushes against the interstellar medium. This area, extending billions of kilometers beyond the planets, is almost unimaginably empty, yet alive with invisible forces, streams of charged particles, magnetic fields, and radiation that define the very boundary of the Sun's domain. Through the 1980s and 1990s, Voyager 1 continued outward, still faithfully transmitting data. NASA engineers periodically adjusted its instruments to detect the subtle changes in the surrounding plasma and magnetic fields, the signs that it was approaching the edge. Scientists expected that somewhere beyond about 100 astronomical units, the distance from the Sun to Earth multiplied by 100, the spacecraft would start to sense the transition from solar space to galactic space. But they didn't know exactly when or how that transition would occur. It took until the early 2000s before Voyager 1 entered what's known as the helios heath, the outermost layer of the heliosphere, where the solar wind slows dramatically after passing the termination shock. Here, the solar wind's speed dropped below the speed of sound in the plasma around it, forming a turbulent zone where charged particles ricocheted back and forth. This was the cosmic frontier, the last shore before open interstellar waters. The data Voyager 1 sent back from this region between 2004 and 2012 were both mysterious and revolutionary. As it moved deeper into the helios heath, Voyager 1 began detecting strange changes. The number of charged particles from the Sun was dropping, while the number of galactic cosmic rays, high-energy particles from outside the solar system, was increasing. But the Sun's magnetic field still dominated the direction of the magnetic lines Voyager measured, which meant it hadn't quite left yet. Scientists around the world watched these readings with fascination and suspense, waiting for the moment when the spacecraft would cross that final, invisible threshold, the heliopause. That moment finally came on August 25, 2012. Voyager 1, then roughly 121 astronomical units from the Sun, or about 18 billion kilometers, crossed into interstellar space. The change was abrupt and unmistakable. Instruments recorded a near-total disappearance of solar wind particles, replaced by a steady influx of high-energy cosmic rays from outside the heliosphere. The density of the surrounding plasma increased dramatically, confirming that Voyager had entered a new environment, one not dominated by the Sun. The spacecraft had become the first human-made object to leave the solar bubble and touch the interstellar medium. What made this achievement so stunning was how long it took: 35 years of continuous flight through a space that's almost entirely empty. Voyager 1 wasn't built to last that long. Its designers had expected perhaps a 5-year mission, maybe 10 at most. Yet, through meticulous management by NASA's Deep Space Network and the remarkable durability of its design, the probe continued functioning decade after decade. By the time it crossed the heliopause, many of the scientists who had launched it were retired, and a new generation had taken up the task of listening to its faint 23-watt signal, a whisper so weak that by the time it reached Earth, it had the power of a single snowflake striking the ground. Crossing into interstellar space didn't mean that Voyager 1 had escaped the solar system entirely. It was still well within the Sun's gravitational influence. But symbolically, it was the moment humanity truly stepped into the galaxy. For the first time, we had a direct sample of the environment between stars. The plasma data confirmed that the space beyond the heliopause is much denser and more energetic than inside the heliosphere, and that the heliopause itself is surprisingly thin, only a few billion kilometers thick, like a cosmic skin separating two vast oceans. Even now, Voyager 1 continues to send home data from this new realm. Its instruments measure cosmic rays, magnetic fields, and plasma waves, helping scientists understand not only our Sun's protective bubble, but also how stellar winds interact throughout the galaxy. The spacecraft's journey has reshaped our understanding of where our solar system ends and where the rest of the galaxy begins. To think that something built in the 1970s, a machine with less computing power than a modern digital watch, has managed to travel for nearly half a century, still doing science, still speaking across the dark, is nothing short of miraculous. When it crossed the heliopause, Voyager 1 didn't just mark the end of one mission, it marked the beginning of humanity's interstellar era. We had, at last, placed our presence in the space between stars. And yet, Voyager 1's journey isn't over. It continues to travel at about 17 kilometers per second, moving ever deeper into the interstellar medium. Its nuclear power source will likely run out sometime in the 2030s, silencing its instruments. But even after that, Voyager 1 will keep moving, a silent ambassador drifting through the galaxy for billions of years. Long after the Earth has changed beyond recognition, long after the Sun itself has faded, Voyager 1 will still be out there, carrying the golden record, carrying our story, and reminding the cosmos that once a small civilization on a pale blue dot dared to reach for the stars. Right now, Voyager 1 is about 24 billion kilometers, roughly 15 billion miles, away from Earth. That number is so large it almost loses meaning when spoken aloud. It's easy to say billions, but to truly comprehend such a distance, you have to break it down. Light itself, traveling at an incredible 300,000 kilometers per second, takes over 22 hours to reach Voyager 1. In other words, every time NASA sends a command to the spacecraft, it takes nearly an entire day for the message to get there, and another day for its response to return. Communication with Voyager is a 2-day conversation across the emptiest stretch of space humanity has ever touched. To put this distance in perspective, the Moon, which feels so far away, is a mere 384,000 kilometers from Earth. The Sun, our life-giving star, is about 150 million kilometers away. Yet Voyager 1 is now more than 160 times farther from the Sun than Earth is. If you could somehow drive there in a car at highway speed, say 100 kilometers per hour, you'd arrive in about 27 million years. Even at the speed of a commercial airliner, the journey would outlast human civilization. Voyager 1 isn't just far from Earth, it's in a realm no human eye will ever see directly, the true interstellar wilderness. But here's the astonishing part. Despite being so far beyond the planets, Voyager 1 is still, in a cosmic sense, homebound. It hasn't actually escaped the Sun's gravity. That might sound surprising, given how far it's traveled. But gravity, unlike the solar wind or magnetic influence, extends infinitely. It weakens with distance, yes, but it never truly reaches zero. The Sun's gravitational domain, known as its Hill sphere, is vast, stretching out more than 1 to 2 light-years in every direction. That's nearly a quarter of the distance to the nearest star. Within that sphere, the Sun's gravitational pull, though faint, still dominates over that of other stars. And Voyager 1 remains deep within that gravitational bubble. This means that technically, Voyager 1 hasn't left the solar system in the full gravitational sense. It has merely left the heliosphere, the region controlled by the Sun's charged particles and magnetic field. To truly escape the solar system's gravitational grasp, a spacecraft would have to travel at or above the solar escape velocity, which from Earth's orbit is about 42 kilometers per second. Voyager 1, fast as it is, travels at about 17 kilometers per second, more than 10 times the speed of a rifle bullet, but not enough to break completely free of the Sun's pull. So, though it's moving away and will never return, the Sun's gravity will still ever so slightly bend its trajectory, keeping it loosely tethered in the Sun's cosmic family forever. This idea, that something can be billions of kilometers away and still belong to the Sun, speaks volumes about the immense reach of our star. Gravity is the quiet architect of the universe, holding entire solar systems together across unimaginable scales. For Voyager 1, that gravitational tether is purely symbolic now. It's so far away that the Sun's pull amounts to little more than a whisper. But it's still there, subtle and eternal. If Voyager 1 were somehow stopped in its tracks, it would, in theory, fall back toward the Sun over the course of many millions of years. Voyager's current distance also highlights just how empty space really is. Even now, it hasn't reached the Oort cloud, that distant halo of icy objects that marks the outermost edge of our solar system. The Oort cloud is thought to begin around 2,000 astronomical units, AU, from the Sun, roughly 300 billion kilometers, and extend perhaps as far as 100,000 AU. By comparison, Voyager 1 is at about 160 AU. That means, even after nearly 5 decades of continuous flight, it has traveled less than 1/10 of the way to the solar system's outermost boundary. At its current speed, it would take more than 300 years just to reach the inner edge of the Oort cloud, and perhaps 30,000 years to exit it entirely. And yet, this slow crawl into the abyss is monumental. For the first time, we have a physical object moving through space that is both of our world and far beyond it. Every kilometer Voyager 1 travels farther is a new record, a new boundary crossed. When its signal finally fades, likely sometime in the 2030s, it will continue coasting through the galaxy silently, a relic of human curiosity. It will pass among the stars, still faintly pulled by the Sun, until other gravitational forces, those of nearby stars, slowly begin to dominate. At that point, perhaps in a few million years, Voyager 1 will drift into another star's realm entirely, becoming part of a new system's story. So when we say Voyager 1 is outside the solar system, we mean it has crossed the border of the Sun's influence of light and wind, not its influence of gravity. It's a subtle but profound distinction, one that reminds us how vast our solar system truly is. Even from 24 billion kilometers away, the spacecraft is still, technically, a child of the Sun, still under its ancient gravitational watch. That invisible connection, a gentle gravitational thread stretching across light days of emptiness, symbolizes something poetic. No matter how far Voyager travels, a tiny fraction of the Sun's pull still clings to it, a silent reminder that everything born in our solar system remains part of its story. And as it sails deeper into the dark, carrying the sounds and symbols of its home world, Voyager 1 continues to embody one of humanity's greatest paradoxes: our endless desire to leave home and our inescapable connection to where we came from. If Voyager 1 is humanity's first ambassador to the stars, its twin, Voyager 2, is the quiet sibling that took a longer, more scenic route through the solar system. While Voyager 1 blazed a fast, direct path outward after visiting Jupiter and Saturn, Voyager 2 embarked on a more complex and breathtaking grand tour, one that gave us our very first close-up views of all 4 gas giants: Jupiter, Saturn, Uranus, and Neptune. This choice of route made Voyager 2 slower to reach the edge of the solar system. It would take 6 more years than Voyager 1 to cross into interstellar space, but it also made it one of the most scientifically valuable missions in the history of space exploration. Voyager 2 was launched on August 20th, 1977, a couple of weeks before Voyager 1, but paradoxically, it ended up following behind its twin. Its trajectory was designed to take advantage of the rare planetary alignment of the late 1970s and 1980s, an alignment that allowed a single spacecraft to visit multiple outer planets through a series of gravity assists. These assists, or slingshot maneuvers, used the massive gravitational pull of each planet to accelerate the spacecraft and bend its path toward the next target, saving enormous amounts of fuel. In a way, Voyager 2 wasn't just flying past planets. It was borrowing their motion to fling itself onward, like a cosmic surfer riding the gravitational waves of the outer solar system. The journey began at Jupiter in 1979, where Voyager 2 captured stunning images of the planet's swirling storms, lightning flashes, and complex ring system. It also discovered new moons and sent back breathtaking footage of Io's volcanic eruptions and Europa's cracked, icy surface, hinting at a subsurface ocean, a possibility that would ignite decades of scientific fascination. Then, in 1981, Voyager 2 reached Saturn, revealing intricate details of the planet's rings and discovering that they weren't uniform bands, but composed of countless particles and waves shaped by the gravitational tugs of nearby moons. It also provided the most detailed images of Saturn's enigmatic moon Enceladus, another world that may harbour a hidden ocean beneath its icy crust. But it was what came next that made Voyager 2 truly historic. Instead of turning upward out of the plane of the planets as Voyager 1 had done, Voyager 2 continued onward to Uranus in 1986, becoming the first, and still the only spacecraft to visit the ice giant. It revealed Uranus as a pale blue-green orb, tipped dramatically on its side, rotating almost perpendicular to its orbit. Voyager 2 discovered 10 new moons, 2 new rings, and even measured Uranus's frigid atmosphere, showing temperatures as low as -224 degrees Celsius. Its instruments also detected a lopsided magnetic field, tilted at an odd angle, a feature that still puzzles scientists today. From Uranus, Voyager 2 pressed on to Neptune, arriving in 1989. Once again, it achieved a first, the only human spacecraft ever to visit that distant, wind-whipped world. The images it sent home were mesmerizing. Neptune's deep cobalt hue, shaped by methane in its atmosphere, immense storms including the famous Great Dark Spot, a massive system nearly the size of Earth, and high-speed winds blowing faster than 2,000 kilometers per hour. The spacecraft also flew past Neptune's moon Triton, revealing active nitrogen geysers, making it one of the few places beyond Earth known to have ongoing geological activity. After Neptune, Voyager 2's planetary mission was complete, but its journey, like Voyager 1's, was far from over. It continued outward, coasting into the far reaches of the solar system. Because its trajectory was slightly slower and more inclined toward the south of the solar plane, Voyager 2's path toward the heliopause, the outer boundary of the heliosphere, took longer. Decade after decade, it moved steadily outward, measuring changes in the solar wind, the interplanetary magnetic field, and cosmic rays. Scientists eagerly compared its readings with those from Voyager 1, which had crossed into interstellar space in 2012. They hoped Voyager 2 would confirm the same phenomena, giving a more complete, three-dimensional view of the Sun's outer bubble. That long-awaited moment came in November 2018, when Voyager 2, then 119 astronomical units from the Sun, roughly 18 billion kilometers away, finally crossed the heliopause. Just as with Voyager 1, its instruments detected a dramatic drop in solar particles and a simultaneous spike in cosmic rays from outside the solar system. But this time, scientists had an advantage they didn't have with Voyager 1. Voyager 2's plasma instrument was still functioning. This allowed for the first direct measurement of the density and temperature of the interstellar plasma. What it found was surprising. The interstellar medium just beyond the heliopause was denser than expected, and the transition region was sharper and thinner than scientists had predicted. This told us that the heliopause might act more like a shield or a skin than a gradual fade-out, a tightly defined border between two very different environments. Voyager 2's crossing also confirmed that the heliosphere isn't symmetrical. Because the Sun moves through the galaxy like a boat through water, the heliosphere is squashed and elongated, compressed on one side, stretched on the other. Voyager 1 and Voyager 2, traveling in different directions, north and south of the solar plane respectively, gave us the first real evidence of this asymmetry. In a sense, they're mapping the Sun's outer frontier from two opposite perspectives, giving humanity its first hints of what the solar system looks like as a whole from the outside. Even though both Voyagers travel at record speeds, tens of thousands of kilometers per hour, their progress emphasizes how staggeringly vast interstellar space truly is. It took Voyager 135 years to reach interstellar space, and Voyager 241 years. These journeys, covering only the tiniest fraction of the distance to the nearest star, highlight the cosmic scale we're dealing with. At their current speeds, each spacecraft would take more than 75,000 years to reach Proxima Centauri, our nearest stellar neighbor. Yet, when you think about it, the fact that both Voyagers are still functioning, still sending signals from beyond the heliopause, is almost unbelievable. Each one transmits a radio signal powered by nuclear decay, carrying precious data about a realm humanity had never encountered before. Together, they've shown us that even at the slow crawl of chemical rockets, we can touch the edge of the interstellar ocean. Their data is rewriting textbooks, refining our understanding of cosmic radiation, and shaping the next generation of deep space missions. Voyager 2's slower, more deliberate journey serves as a beautiful counterpoint to Voyager 1's direct dash into the dark. It reminds us that exploration isn't always about speed. Sometimes it's about depth, patience, and persistence. Where Voyager 1 gave us our first step into interstellar space, Voyager 2 gave us the full portrait of the solar system on the way there. A tour that revealed the diversity and wonder of our planetary family before crossing into the galaxy beyond. And now, like its twin, Voyager 2 continues to drift farther into interstellar space, more than 22 billion kilometers from Earth and counting, still whispering faint messages home across the void. Together, these two spacecraft mark the edge of everything we've ever known, showing us how far human curiosity can truly reach. They are not just machines, they are symbols of endurance, proof that even across unimaginable distances, a tiny voice from Earth can still be heard among the stars. Despite having traveled farther than any object ever created by human hands, Voyager 1's speed is, in the grand theatre of the cosmos, astonishingly slow. It moves through the interstellar darkness at about 17 kilometers per second, or roughly 61,000 kilometers per hour. On Earth, that kind of speed is breathtaking. It could circle our planet in less than 40 minutes. But when measured against the infinite canvas of space, the scale of stars, light years, and galaxies, that blistering pace shrinks to something almost comically sluggish. Compared to the distances it must cover, Voyager 1 is, in effect, a snail crawling across a football field, inching forward through a void so vast that even light itself, the ultimate speed limit of the universe, would take years to cross the nearest cosmic distances. To understand just how slow 17 kilometers per second really is, consider this. Light covers nearly 300,000 kilometers in a single second. That means for every second light travels, Voyager 1 advances only about 1/10,000th of that distance. If the Sun were at one end of a football field and the nearest star, Proxima Centauri, were at the other, light would sprint the entire length of that field in just over 4 seconds. Voyager 1, at its present speed, would take more than 75,000 years to reach the far goalpost. Its velocity, which seems impossibly fast to us, is nearly motionless on the galactic scale, a testament to how immense space truly is. Still, maintaining that speed for nearly half a century is no small feat. When Voyager 1 left Earth's orbit, it wasn't just flung into space by a powerful rocket and left to coast. It gained its enduring momentum through a precise series of gravity-assist maneuvers, primarily from Jupiter and Saturn. Those flybys acted like cosmic slingshots, each encounter bending Voyager's trajectory and adding to its speed. Without those planetary assists, the probe would never have reached interstellar space in the lifetime of humanity. What's remarkable is that these assists weren't powered by fuel, but by the gravitational energy of the planets themselves. A brilliant exploitation of celestial mechanics that turned the outer worlds into stepping stones to the stars. Voyager 1's 17 kilometers per second may seem slow compared to light, but compared to any other spacecraft we've ever launched, it's astonishing. For instance, the Apollo missions that carried astronauts to the Moon traveled at about 11 kilometers per second relative to Earth, fast enough to break free of Earth's gravity, but still far short of interplanetary speeds. The New Horizons probe, which flew past Pluto in 2015, left Earth faster than any spacecraft before it, at 16.26 kilometers per second. But even that blistering departure speed eventually decreased as it climbed away from the Sun's gravitational pull. Voyager 1, however, gained permanent speed boosts from its planetary encounters, allowing it to maintain a steady outward velocity that continues to carry it deeper into the galaxy. The paradox of Voyager's motion is that although it's racing outward endlessly, it will never truly stop, nor will it ever arrive. In interstellar space, there are no brakes, no friction, no air resistance. Voyager 1's speed will remain almost constant for millions of years, gradually altered only by the gentle tug of gravity from passing stars or clouds of gas. The concept of slowing down doesn't exist out there. Once set in motion, it will continue to glide silently, forever. This is one of the most haunting aspects of space exploration. Even at tens of thousands of kilometers per hour, we move through the cosmos at a crawl. The nearest star system, Alpha Centauri, is about 4.24 light-years away, some 40 trillion kilometers. At Voyager 1's pace, it would take those 75,000 years to make the trip, longer than all of recorded human history. By the time it reached another star, humanity, and perhaps even Earth itself, could be unimaginably different. The sheer slowness of this journey isn't a failure of technology, but a reflection of the immense challenge of interstellar travel. Our rockets rely on chemical propulsion, a method bound by physics that gives us only a small fraction of the energy required to reach truly cosmic speeds. Every kilogram of fuel carries limited thrust, and the more fuel you bring, the heavier your spacecraft becomes, demanding even more fuel to move it. It's a vicious cycle that makes achieving higher velocities exponentially more difficult. That's why Voyager 1, despite being a triumph of engineering, still drifts like a feather on the cosmic wind compared to the distances it must cover. And yet, this snail's pace is still enough to break boundaries no other craft has crossed. Every second, Voyager 1 puts another 17 kilometers between itself and the Sun. Every minute, it adds more than 1,000. Every hour, it travels farther than the distance from New York to Tokyo, and it's been doing this for nearly 5 decades without rest. That relentless motion, imperceptible on any human scale, yet unstoppable across millennia, is the quiet poetry of spaceflight. Steady persistence, conquering the infinite. Voyager 1's slow, eternal journey reminds us of our cosmic perspective, that speed, like distance, is relative. What feels impossibly fast to us is barely a whisper of motion in the galaxy's vast expanse. And yet, despite this, we have managed to touch interstellar space with our fragile machines. We've proven that even moving at a crawl, persistence and ingenuity can carry us farther than imagination once allowed. That slow, faithful crawl through the stars sets the stage for the next great question. If Voyager 1 takes 75,000 years to reach the nearest star, what would it take to get there faster? This leads us to the staggering challenge of interstellar travel itself, the cosmic race between speed, distance, and time that defines the future of exploration. If Voyager 1 could somehow aim itself directly toward our nearest stellar neighbor, Proxima Centauri, it would still take more than 75,000 years to arrive. That's 75 millennia, a span of time so vast that it's almost impossible for the human mind to fully comprehend. To put that into perspective, 75,000 years ago, modern humans were sharing the Earth with Neanderthals, mammoths roamed across Europe, and the first cave paintings had not yet been made. Civilizations would rise and fall countless times before Voyager 1 reached another sun. By then, continents would have shifted, languages and nations would have long vanished, and our descendants might not even recognize the world we live in today. At Voyager 1's current speed, 17 kilometers per second, it's moving faster than any bullet, faster than any spacecraft humanity has ever built. Yet in the face of interstellar distances, that velocity barely registers. Proxima Centauri, the closest star to our Sun, lies about 4.24 light-years away, or roughly 40 trillion kilometers. If you were to drive that distance in a car at 100 kilometers per hour, it would take you more than 45 billion years, roughly 10 times the age of the universe. Even light, the fastest thing known to science, takes over 4 years to make the journey. So for a spacecraft like Voyager 1, powered by physics we understand and engines we can actually build, the trip is simply enormous beyond imagination. Let's try to visualize it another way. Imagine shrinking the entire solar system so that the Sun and its planets fit within a small classroom. On this scale, Voyager 1 would already be outside the walls, floating somewhere in the schoolyard. But the nearest star system, Proxima Centauri, would still be dozens of kilometers away, perhaps in another city entirely. That's how staggeringly far even the nearest star truly is. The solar system, vast as it seems, is just a tiny oasis floating in an almost infinite desert of space. What's fascinating is that Voyager 1 is technically headed in the general direction of the constellation Ophiuchus, which is near the celestial region that contains Proxima Centauri. However, it's not precisely aimed toward it, and even if it were, there's no practical way to alter its course now. Voyager's thrusters were designed only for minor adjustments, not long-term navigation across light years. Even if it were perfectly aligned, it would still be tens of thousands of generations before it reached that faint red star. This incredible timescale illustrates just how slow interstellar travel really is with current technology. Even if we could somehow double Voyager's speed to 34 kilometers per second, the journey would still take around 37,500 years. Multiply its speed by 10, an unimaginable feat with current propulsion, and you'd still be looking at 7,500 years. These are spans of time that dwarf all of human history. Every myth, empire, invention, and dream of our species fits within a fraction of that journey, and that's only the nearest star. The Milky Way galaxy contains around 400 billion stars, spread across a diameter of about 100,000 light-years. That means, at Voyager 1's speed, it would take roughly 20 billion years just to cross our galaxy, longer than the universe has even existed so far. When we talk about interstellar space, then we're not just talking about a region beyond the Sun's influence. We're talking about a scale so vast that even our greatest machines are like dust motes drifting on an endless cosmic tide. Still, even though Voyager 1 will never reach another star within any human time frame, its journey is far from meaningless. Every kilometer it travels carries our name a little farther into the galaxy. It is the first human-made object to truly step beyond the boundary of our solar system, the first artifact to swim in the interstellar current that flows between the stars. And though it won't come close to another star in our lifetimes, the very fact that it will, someday, in tens of thousands of years, drift through another star's neighborhood is profoundly poetic. It means that something we made, a product of human hands and dreams, will one day pass silently through a region of the galaxy we can only imagine. Scientists have even tried to calculate which star system Voyager 1 might approach in the distant future. Based on its trajectory, it's expected to come within about 1.6 light-years of a small star in the constellation Camelopardalis. But not for another 40,000 years. At that time, its instruments will long be dead, its power source cold, its signals silent. Yet it will still be traveling, carrying the golden record, that fragile, gold-plated disc engraved with sounds, images, and greetings from Earth. If any distant civilization ever finds it, they'll discover a message from a world that no longer exists in the form it once did. A cosmic time capsule drifting through the deep. This reality, that our fastest spacecraft would need tens of millennia to reach even the nearest star, is humbling. It underscores both the grandeur of the universe and the limits of our current technology. Every scientific advancement in propulsion, from nuclear engines to ion drives to light sails, is aimed at overcoming this vast, merciless distance. Voyager 1 reminds us how far we've come, but also how far we still have to go before interstellar travel becomes anything more than a dream. And yet, there's something profoundly human about this slow, eternal voyage. Voyager 1 isn't just a spacecraft. It's a symbol of endurance. It represents our refusal to be confined by distance or time. Even if it takes 75,000 years to reach another star, even if no one is alive to see it happen, the fact that we sent it, that we dared to try, is what matters. It's proof that humanity, for all its fragility, is capable of creating something that lasts longer than memory, longer than civilization itself. Voyager's slow crawl toward Proxima Centauri isn't a failure of speed, it's a triumph of persistence. It tells us that exploration doesn't always happen in leaps and bounds, but in steady, silent motion through the dark. And though we may never ride alongside it, we know it's out there, a tiny, persistent echo of human curiosity, traveling across the cosmos at 17 kilometers per second, carrying our story toward the stars. While Voyager 1 and 2 continue their lonely trek into the interstellar dark, they're not the only human-made explorers venturing toward the edge of our solar system. Decades after their launches, another spacecraft joined the journey, one designed for a new generation of exploration, equipped with cutting-edge technology and built to go faster than any probe before it. This was New Horizons, NASA's mission to Pluto and beyond, launched in January 2006. When it left Earth, it broke records as the fastest spacecraft ever launched, speeding away from our planet at over 58,000 kilometers per hour, roughly 16 kilometers per second. For comparison, that's fast enough to travel from New York to London in under 7 minutes. Yet, despite that incredible velocity, the cold truth remains. Even at that speed, it will take another 50 to 70 years for New Horizons to reach the heliopause, the same boundary Voyager 1 crossed back in 2012. New Horizons was designed with a singular, audacious goal: to complete humanity's first flyby of Pluto, the most mysterious of the classical planets and the first representative of the Kuiper Belt, a vast ring of icy bodies and dwarf planets that orbit far beyond Neptune. For decades, Pluto had been a point of fascination and frustration for astronomers. We knew it existed, but even our most powerful telescopes could only glimpse it as a tiny, blurry speck. When New Horizons was conceived, we had no detailed images of its surface, no clear idea of its composition, and no understanding of its atmosphere. The spacecraft was humanity's chance to visit the last uncharted world of the traditional solar system map. After a 9.5-year journey, New Horizons finally reached Pluto on July 14, 2015, delivering a spectacle that exceeded every expectation. As it approached the dwarf planet, the spacecraft began sending back the first close-up images ever taken. and what those pictures revealed stunned scientists and the public alike. Pluto wasn't just a frozen dead rock in space. It was a surprisingly complex and dynamic world. Its surface showed mountains made of water ice towering as high as the Rockies, smooth nitrogen plains that looked freshly resurfaced, and even hints of glacial movement. The heart-shaped region, now famously known as Tombor Regio, named for Clyde Tombaugh, Pluto's discoverer, became an instant symbol of exploration. It told us that even on the frozen fringes of the solar system, nature's creativity persists. In the hours and days following the flyby, New Horizons captured over 50 gigabits of data, including detailed maps, atmospheric readings, and stunning images of Pluto's moons, particularly Charon, a moon so large that Pluto and Charon actually orbit a point in space between them, forming a true binary system. The data took more than 15 months to transmit back to Earth, a testament to the immense distances involved. Each signal, traveling at the speed of light, took nearly 5 hours to reach us. That's how far from home this little probe had ventured. But Pluto was never meant to be the end of New Horizons' mission, only its first destination. After the successful flyby, NASA extended the mission into the Kuiper Belt, aiming for a new target, Arrokoth, previously known as 2014 MU-69. In January 2019, New Horizons made history again by performing the most distant flyby ever conducted, nearly 6.6 billion kilometers from Earth. Arrokoth, a snowman-shaped world just 36 kilometers long, turned out to be one of the most primitive objects ever studied, a time capsule from the dawn of the solar system. Its ancient, undisturbed surface offered a glimpse into how the planets themselves formed more than 4.5 billion years ago. Now, New Horizons continues to travel outward at nearly 14.5 kilometers per second, a little slower than Voyager 1, but still faster than any other active probe. Even at this incredible speed, the scale of space means its journey to the heliopause, the boundary where the sun's solar wind gives way to the interstellar medium, will take another 50 to 70 years. Scientists estimate that it will cross into interstellar space sometime between 2060 and 2080, depending on fluctuations in the size of the heliosphere. Until then, New Horizons remains firmly within the Sun's domain, sailing through the Kuiper Belt, studying the faint cosmic dust, and measuring the charged particles that fill this faraway region. It's also observing the cosmic background light, the faint glow left over from stars and galaxies, to better understand the structure of our universe. Each bit of data it sends home expands humanity's understanding of what lies beyond the planets, in the vast, icy frontier that surrounds us. What's remarkable about New Horizons is that, despite being launched nearly 30 years after the Voyagers, its fate will mirror theirs. It, too, will eventually drift into interstellar space, joining Voyager 1 and 2 as silent travelers carrying messages from Earth. However, unlike the Voyagers, New Horizons doesn't carry a golden record. Its legacy will live in its discoveries, in the images and insights that forever changed how we view the outer solar system. The comparison between Voyager and New Horizons also underscores just how relentlessly vast our solar system is. Even with technology decades more advanced and a launch speed far greater than anything the 1970s could produce, New Horizons still requires more than half a century to reach the same boundary Voyager 1 crossed years ago. It's a powerful reminder that, in the grand scale of the cosmos, even our fastest spacecraft crawl forward inch by inch. Still, that slow progression is profound. Each of these missions, Voyager 1, Voyager 2, and New Horizons, represents a chapter in humanity's growing reach into the stars. They are 3 tiny points of light moving ever outward, carrying the fingerprints of human curiosity. Together, they form the vanguard of our species' exploration. a testament to our enduring desire to push past every known horizon. And as New Horizons continues its silent journey through the Kuiper Belt, it sets the stage for an even greater challenge: the question of what it truly takes to escape the Sun's gravity entirely. Because even though these spacecraft are far beyond the planets, they're still bound, however faintly, by the Sun's pull. To truly leave home forever, a spacecraft must do more than cross the heliopause. It must achieve the speed needed to break free of the Sun's gravitational hold. That concept, solar escape velocity, defines the next threshold in our quest to go beyond the solar system once and for all. The farther we send our spacecraft from home, the more we begin to appreciate the invisible power that binds everything in our solar system together: gravity. The Sun's gravitational influence doesn't simply end where the planets stop. It stretches across trillions of kilometers, a vast and unyielding tether that keeps every object in its grip, from the massive gas giants to the tiniest comet. To truly leave the solar system, not just cross the heliopause or drift beyond the planets, a spacecraft must break free of that gravitational hold entirely. This requires reaching what's known as solar escape velocity, the speed needed to overcome the Sun's pull forever. From Earth's orbital distance, roughly 150 million kilometers from the Sun, the solar escape velocity is about 42 kilometers per second, or around 150,000 kilometers per hour. That means a spacecraft must travel at that speed relative to the Sun to escape its gravity completely and coast endlessly into interstellar space without ever being drawn back. To put that in perspective, that's nearly 4 times faster than Earth's own escape velocity of 11.2 kilometers per second, the speed a rocket needs to leave our planet's gravity well. It's an almost unimaginable pace, about 120 times faster than a commercial jet, and still far slower than the speed of light. So far, no spacecraft ever launched by humanity has fully achieved solar escape velocity directly from Earth. The reason isn't that we lack the technology to reach such speeds in bursts. Our rockets can generate incredible thrust, but because of the limitations of fuel, mass, and physics. Every kilogram of fuel adds weight, which requires more energy to move, which in turn demands even more fuel, a vicious cycle that quickly becomes impossible to sustain. The larger the spacecraft and the farther you want to go, the harder it becomes to accelerate it fast enough to break free. Most spacecraft, instead of attempting to reach such speeds directly, rely on a combination of initial launch velocity and gravity assists from planets to gradually increase their speed. Gravity assists, sometimes called slingshot maneuvers, are a clever way to steal a bit of momentum from a planet's orbital motion around the Sun. As a spacecraft flies past a planet like Jupiter or Saturn, it falls into its gravity well, accelerates, and then escapes on a new trajectory, moving faster than before. This technique allows us to achieve interplanetary speeds that would be impossible using fuel alone. Both Voyager probes, for example, gained enormous speed from their encounters with the gas giants, flinging them toward the outer solar system on paths that would carry them farther than any previous mission. However, even with these boosts, Voyager 1, our fastest outward-bound spacecraft, travels at about 17 kilometers per second relative to the Sun, far short of the 42 kilometers per second needed to break free completely. In fact, if it somehow stopped receiving tiny gravitational nudges from the planets and other celestial objects, the Sun's pull would still keep it loosely bound, tugging gently but persistently as it drifts. It will never fall back, of course, because it's already moving outward at escape speed relative to Earth's orbit. But it will always remain under the faint influence of our star. This distinction between crossing the heliopause and achieving true gravitational escape is subtle but profound. The heliopause marks the boundary of the Sun's magnetic influence, the point where the solar wind gives way to the interstellar medium. But gravity, unlike the solar wind, doesn't fade away so easily. It has an infinite reach. Even billions of kilometers away, even far beyond the planets, the Sun's gravity still defines the orbits of comets in the distant Oort cloud, a vast shell of icy bodies that extends perhaps a light-year or more from the Sun. To escape that entirely would require a level of speed and energy far beyond anything our current propulsion systems can provide. So why haven't we designed spacecraft that can achieve it? The answer lies in trade-offs. Missions are always a balance between speed, payload, cost, and purpose. To send a spacecraft out of the solar system at 42 kilometers per second would require either an enormous rocket capable of generating sustained acceleration, which would be prohibitively expensive and technologically complex, or an entirely new kind of propulsion system, such as a nuclear fusion drive, antimatter engine, or laser-powered light sail. Each of these concepts has been studied in theory, but remains beyond practical realization today. There's also the issue of scientific opportunity. Once a probe achieves full solar escape velocity, it leaves the Sun's neighborhood permanently. That means no more planetary flybys, no more chances to study the outer solar system in detail. Most missions, like Voyager, Pioneer, and New Horizons, were designed to gather as much science as possible on their way out, using the gravity of planets to slingshot onward, yes, but also to observe them closely. Their slower escape speeds were a deliberate trade-off. They allowed the spacecraft to linger, to explore, to observe. In a sense, we chose knowledge over haste. And there's one more crucial reason: efficiency over eternity. Even if a probe were launched fast enough to completely escape the Sun's gravity, it wouldn't necessarily matter for tens of thousands of years. At cosmic scales, even full escape velocity doesn't make you much faster in terms of reaching the next star. Whether it takes 75,000 years or 60,000 years to reach Proxima Centauri, both timelines are still far beyond any meaningful human duration. Until we develop technologies that can reach a significant fraction of the speed of light, solar escape remains more symbolic than practical. Still, the concept captures something deeply inspiring. Solar escape velocity isn't just a number. It's the threshold between belonging and freedom. Every spacecraft we've ever launched is, in some sense, still part of the Sun's story, orbiting, however loosely, within its infinite reach. To exceed 42 kilometers per second would mean crossing a one-way frontier, leaving our star's gravity forever, becoming a true interstellar traveler. That idea has haunted and inspired scientists and dreamers alike. It's the benchmark that future generations will aim to surpass, the speed that marks the difference between being a visitor to the cosmos and becoming part of it. And as we contemplate that goal, it naturally leads us to one of the most ingenious techniques ever devised to push our spacecraft closer to that dream: the use of gravity assists, the celestial dance moves that allowed tiny machines like Voyager to gather speed and steal just enough energy from the planets to begin their impossible journey toward the stars. One of the most remarkable and elegant tricks in all of space exploration, one that made the Voyager missions, New Horizons, and countless other interplanetary journeys possible, is the technique known as gravity assist, or the gravitational slingshot. It's a maneuver so deceptively simple in concept, yet so powerful in execution, that it allows a spacecraft to gain enormous amounts of speed without using any additional fuel. In essence, it's the art of stealing a tiny bit of momentum from a planet as you pass by it, using its gravity like a cosmic catapult to hurl a spacecraft faster and farther into space. To understand how this works, imagine a small spacecraft approaching a massive planet like Jupiter. As it nears the planet, the spacecraft falls into its gravitational field. It begins accelerating toward it, gaining speed just like a stone dropped toward Earth. But instead of plunging into the planet, the spacecraft passes close by, swinging around the planet and then flying off in a new direction. From the spacecraft's point of view, it has simply fallen toward Jupiter, looped around it, and escaped again, all according to the predictable laws of gravity. However, from the Sun's point of view, something magical has happened. When the spacecraft exits Jupiter's gravitational pull, it's now moving faster relative to the Sun than it was when it entered. That extra speed comes from the planet's own orbital motion around the Sun. Every planet moves at incredible velocities. For instance, Jupiter travels around the Sun at about 13 kilometers per second. When a spacecraft approaches a planet in the right direction, in front of the planet's orbital path, it can effectively borrow a tiny amount of that motion. The planet, in turn, loses an infinitesimal bit of its orbital energy, an amount so small that it's utterly undetectable, while the spacecraft gains a tremendous boost. It's like catching a moving train and jumping off again, propelled forward by its motion. This technique is what made the Voyager missions possible. When Voyager 1 and Voyager 2 were launched in 1977, they were sent on carefully calculated paths designed to take advantage of a once-in-a-lifetime alignment of the outer planets, an event that occurs only once every 176 years. Jupiter, Saturn, Uranus, and Neptune were arranged in such a way that a single spacecraft could visit them all in one continuous journey, using each planet's gravity to slingshot toward the next. This concept was called the Grand Tour, and it was one of the most audacious engineering feats in human history. Voyager 1, for example, first flew past Jupiter in 1979. As it approached the giant planet, Jupiter's immense gravity pulled the spacecraft inward, accelerating it dramatically. Voyager passed just 350,000 kilometers above the planet's cloud tops, close enough to feel Jupiter's titanic gravitational tug. As it swung around and away, that acceleration was converted into an outward velocity, propelling it towards Saturn at speeds that would have been impossible to achieve with any rocket alone. In that single maneuver, Voyager 1 gained roughly 10 kilometers per second of additional speed relative to the Sun, the equivalent of what would have required thousands of kilograms of fuel if done by propulsion. Voyager 2 performed a similar trick, though its trajectory was more complex. After its encounter with Jupiter, it slingshotted onward to Saturn, where it repeated the process, diving close to the ringed planet, stealing a bit more of its orbital momentum, and redirecting its path toward Uranus and eventually Neptune. Each planet effectively handed off the spacecraft to the next, accelerating it along a winding, elegant path through the outer solar system. These gravity assists didn't just add speed, they also changed direction, bending Voyager's flight path without requiring any engine burns. The entire journey was choreographed with breathtaking precision, like a celestial ballet, with planets as partners and gravity as the music. The beauty of the gravity assist technique lies in its efficiency. Space travel is brutally constrained by fuel. Every extra kilogram of propellant adds mass, and every bit of mass demands even more fuel to move it. Traditional propulsion systems can't sustain acceleration for long. Rockets burn furiously for minutes and then coast for decades. Gravity assists, by contrast, provide free energy. Or more precisely, they exchange energy between the spacecraft and the planet in a way that conserves the total energy of the system. The planet loses an imperceptible fraction of its orbital momentum, while the spacecraft gains a huge leap forward. It's one of those rare tricks where physics feels almost like magic. And it isn't just the Voyagers that have used it. Many of humanity's most ambitious missions have relied on gravity assists to reach their destinations. The Galileo spacecraft used Earth and Venus to gain speed toward Jupiter. Cassini, the legendary mission to Saturn, performed multiple flybys of Venus, Earth, and Jupiter to build up the velocity it needed. Messenger, which orbited Mercury, actually had to lose speed, so it used repeated flybys of Earth, Venus, and Mercury itself to slow down enough to be captured by Mercury's gravity. And New Horizons, on its way to Pluto, performed a stunning gravity assist at Jupiter in 2007 that boosted its speed by nearly 14,000 kilometers per hour, shaving 3 years off its journey. Every successful gravity assist requires precise timing and alignment. If a spacecraft arrives at the wrong angle, or too early or late, it can miss the opportunity entirely or be flung in the wrong direction. These maneuvers are calculated years, sometimes decades, in advance, requiring deep understanding of celestial mechanics. The spacecraft's trajectory must thread through a moving target, planets hurtling around the Sun at tens of thousands of kilometers per hour. It's a testament to human ingenuity that we can plan and execute such delicate maneuvers across billions of kilometers of empty space. Without gravity assists, the Voyagers would never have reached the outer planets, and the New Horizons probe might still be en route to Pluto today. These techniques are what make interplanetary, and someday, perhaps interstellar, exploration possible within the limits of our technology. They allow us to turn the motions of the planets themselves into a kind of propulsion system, using the machinery of the solar system to extend our reach beyond it. And yet, as powerful as gravity assists are, they have their limits. Each planet can only offer so much speed, and there's only so much alignment we can exploit. The Voyagers, after their encounters, reached speeds that would carry them to the stars, but still at a crawl compared to the cosmic scale. To go beyond, to reach the stars in anything less than millennia, will need something far faster, something that doesn't depend on gravity, fuel, or chance alignments. That's where the next generation of visionary ideas comes in. Concepts like breakthrough Starshot and light sail propulsion, which aim to send tiny probes hurtling across the galaxy at a significant fraction of the speed of light. These aren't science fiction anymore, but real projects being studied today. If gravity assists are the poetry of orbital motion, these future drives are the promise of a new era, one where humanity might finally travel between the stars, not in tens of thousands of years, but in mere decades. As awe-inspiring as the Voyagers and New Horizons are, their epic but glacial pace reveals the truth of interstellar travel, that, with our current propulsion technology, the stars are impossibly far. A journey to even the nearest one, Proxima Centauri, takes tens of thousands of years at Voyager's speed. This staggering timescale has driven scientists, engineers, and dreamers alike to imagine new kinds of missions, ones that might break the limitations of chemical and gravitational propulsion entirely. Among these bold ideas, one concept stands out for both its audacity and its grounding in real physics. Breakthrough Starshot, a project that envisions sending tiny spacecraft to another star system within a single human lifetime by reaching speeds of up to 20% the speed of light. The Breakthrough Starshot initiative was publicly announced in 2016, backed by billionaire philanthropist Yuri Milner, with scientific guidance from the late Stephen Hawking and other prominent physicists. Its goal is breathtaking in its simplicity: to launch a fleet of miniature wafer-sized spacecraft, known as starships, attached to ultra-thin light sails, and to accelerate them to relativistic speeds using powerful ground-based lasers. Each of these tiny probes, no larger than a postage stamp, would be equipped with miniature cameras, sensors, and communication systems. Once deployed, they could be accelerated to around 60,000 kilometers per second, or about 20% the speed of light, allowing them to reach the Alpha Centauri star system in just 20 to 25 years. To grasp how revolutionary this is, consider the comparison. Voyager 1, the fastest outward-bound spacecraft we've ever built, would take 75,000 years to cover the same distance. breakthrough Starshot's probes could do it within a single generation. Humanity would, for the first time, be capable of sending something across the interstellar gulf and receiving data back within a lifetime. It would transform our relationship with the cosmos from one of distant observation to one of direct exploration. The underlying principle of laser-powered light sail propulsion is both elegant and challenging. Traditional spacecraft carry their own fuel, but that fuel adds weight, and the heavier a craft becomes, the harder it is to accelerate. Starshot proposes the opposite, a craft with no onboard fuel at all, relying instead on external propulsion from Earth. The idea is to mount a massive phased array of lasers, possibly covering several square kilometers of desert or mountaintop, capable of producing hundreds of gigawatts of power. These lasers would focus their beams onto the sail of each tiny spacecraft, made of an incredibly lightweight and reflective material, perhaps graphene or a specially engineered dielectric film. As the laser light reflects off the sail, it transfers momentum, much like wind pushing a sailboat, but using photons instead of air. Since light travels at incredible speed, even the tiny momentum of individual photons adds up when trillions strike the sail per second. Over the course of just a few minutes, this constant pressure could accelerate a gram-scale spacecraft to 20% of the speed of light, nearly 60,000 kilometers per second, before the laser shuts off and the craft continues coasting through interstellar space. At that speed, the spacecraft would pass the Moon in just over a second, reach Mars in under an hour, and clear Pluto's orbit in a single day. It would cover the distance that took Voyager more than 4 decades to achieve in less than 3 days. Such a mission would completely redefine our concept of exploration. Instead of waiting centuries or millennia for interstellar travel, we could potentially reach another star and take close-up images of alien worlds orbiting it, all within a single human lifetime. But the challenges are immense. For one, building a laser array powerful enough to deliver that kind of thrust would require technological advances on a planetary scale. The array would need to combine thousands of synchronized lasers, all perfectly phased, to focus a beam across millions of kilometers with extreme precision. Even the tiniest atmospheric disturbance or a single misalignment could disrupt the process. Then there's the issue of heat, both in the lasers themselves and on the sail, which would need to withstand the intense bombardment of photons without vaporizing. And that's just the beginning. Once the spacecraft reaches interstellar speeds, it faces the merciless reality of the interstellar medium. Not empty, but filled with stray particles of gas and dust. At 20% the speed of light, even a grain of sand could obliterate a probe on impact. Engineers have proposed that the sails might double as shields, using their forward edges to deflect or vaporize particles before they can cause damage. But this remains one of the biggest engineering uncertainties. Communication poses another problem. Even if a probe reaches the Alpha Centauri system intact, transmitting data back to Earth across 4.24 light-years is no small feat. The signal, incredibly faint by the time it arrives, would require a receiver network of extraordinary sensitivity, perhaps even the same laser array used for launch, now reversed to detect the returning data beams. And with such small payloads, every bit of data would need to be compressed, optimized, and possibly transmitted in brief, carefully timed bursts. Despite these challenges, breakthrough Starshot represents a turning point in how we think about space exploration. For the first time, scientists are seriously studying methods that break free from the tyranny of rockets, technologies that harness pure light instead of propellant. While the concept is still in early theoretical stages, the necessary technologies are slowly converging. Miniaturization of electronics, advances in laser systems, and materials. Science innovations are all moving toward making such missions feasible, perhaps by the middle of the 21st century. What's even more exciting is that the Starshot concept doesn't just apply to distant stars. It could also revolutionize exploration within our own solar system. A laser sail system could send lightweight probes to Mars in days, to the outer planets in weeks, or to the Kuiper Belt in a matter of months. We could deploy fleets of miniature explorers, each capable of collecting data and relaying it home, turning the solar system into a living, connected laboratory. Starshot isn't the only vision of fast interstellar travel. Other concepts, such as fusion propulsion, antimatter drives, and nuclear pulse propulsion, have been proposed, each with their own advantages and risks. Fusion engines, for instance, could theoretically achieve speeds up to 10% of light, though the engineering hurdles of controlling sustained fusion remain enormous. Antimatter drives could be even more powerful, but antimatter itself is extraordinarily difficult and expensive to produce and store safely. Compared to these, laser-powered light sails offer a simpler, scalable approach, one that doesn't require massive onboard reactors or dangerous materials, only precision and patience. At its heart, Breakthrough Starshot is not just a mission concept, it's a philosophical statement. It says that interstellar travel doesn't have to belong to the distant future. It's not a fantasy confined to science fiction novels. It's a problem that might be solved with creativity, persistence, and the physics we already understand. If the Voyagers were our first whispers into the cosmic ocean, then Breakthrough Starshot could be our first leap. A leap not powered by fire and fuel, but by light itself. The same light that has guided humanity since the dawn of time. And yet, even at 20% the speed of light, there are limits. The journey to another star in 20 years is a monumental achievement. But to go faster, to reach the galaxy beyond our nearest neighbors, would require mastering even more extreme technologies. Before we dream of those, though, it's worth looking at what such speed really means. How drastically travel times change with even small increases in velocity, and how close we could come to traversing the interstellar gulf if we could harness just a fraction of light's true speed. The difference between traveling at 20% the speed of light and at the current speeds of our fastest spacecraft is nothing short of staggering, not just in numbers, but in how it reshapes our understanding of time, distance, and possibility. The speed of light, about 300,000 kilometers per second, is the ultimate speed limit of the universe, the fastest anything can move through space. And yet, even a small fraction of that speed transforms interstellar travel from a multi-generational dream into something achievable within a single lifetime. Let's take our closest neighbor, Proxima Centauri, located about 4.24 light-years away, roughly 40 trillion kilometers. At Voyager 1's current velocity of 17 kilometers per second, that journey would take around 75,000 years. To put that in perspective, when Voyager 1 finally arrived, it would be nearly the year 77,000 AD. Continents would have shifted, mountain ranges would have eroded, and whatever humanity has become by then may no longer even remember the probe's existence. Voyager 1, though blazing through space faster than anything we've ever built, is still crawling across the galaxy at a cosmic snail's pace. Now, let's imagine we could move faster, even just a little faster in percentage terms, and see how dramatically the travel times change. At 1%, the speed of light, 3,000 kilometers per second, that same journey to Proxima Centauri would take about 424 years. That's still longer than any human civilization has existed, but suddenly, it's a time frame we can grasp historically. 4 centuries ago, Galileo was just beginning to look through his telescope. If we had launched a spacecraft then, traveling at 1% of light speed, it would be arriving around now, a mind-bending thought. At 5% of light speed, 15,000 kilometers per second, the travel time drops to 85 years. That's less than a single human lifetime. It means that a mission launched by one generation could potentially be completed and studied by the next. Suddenly, interstellar travel begins to feel personal. If a probe like this were sent out today, it could be passing through the Proxima Centauri system before the end of the 22nd century. Humanity could actually witness the results. And then there's 20% of light speed, the ambitious target of the breakthrough Starshot initiative. At that astonishing pace, the same trip would take just a little over 20 years. Imagine it. We could launch a probe toward another star today, and by the 2040-50s or 2050-50s, we might receive its first images and data from an alien solar system. In cosmic terms, that's instantaneous. For the first time, interstellar exploration wouldn't be an abstract, far future dream. It would be a tangible reality within our own lifetimes. To appreciate what that means, think about how far we've come technologically in just the last 20 years. 2 decades ago, the iPhone didn't exist. The International Space Station was in its infancy. The first exoplanets had only just been discovered. In another 20 years, we could be looking at high-resolution images of planets orbiting another star, perhaps even identifying one that shows signs of life. That's the scale of transformation that relativistic travel, even at a fraction of light speed, could unlock. The difference between these travel times illustrates a profound truth about the exponential nature of velocity in space. Every incremental increase in speed pays enormous dividends in distance and time. Doubling your speed doesn't just halve your travel time, it can shrink centuries into decades. But achieving those increments is no easy feat. The faster you go, the more energy you need, and not linearly, but exponentially. The kinetic energy required to accelerate an object increases with the square of its speed. That means it takes 4 times as much energy to double your velocity. To reach 1% of light speed, the energy demands are already astronomical. To reach 20%, they border on the unimaginable by today's standards. Let's put that into numbers. Accelerating a 1-gram probe, the kind envisioned for breakthrough Starshot, to 20% of light speed would require roughly 300 terajoules of energy, the equivalent of what the entire United States consumes in electricity in about 10 minutes. Now imagine trying to do that for a spacecraft weighing several tons. The numbers spiral beyond anything achievable with chemical rockets or even nuclear propulsion. That's why light sail technology, or other external propulsion methods, are so vital. They shift the burden of energy generation away from the spacecraft itself. At these higher speeds, other challenges emerge as well. For instance, at 20% of light speed, even tiny dust particles in interstellar space become dangerous projectiles. A single grain of sand, only a millimeter wide, would hit with the energy of a small bomb. That means future high-speed spacecraft would need advanced shielding, perhaps electromagnetic fields or sacrificial layers designed to vaporize or deflect oncoming particles. Communication, too, becomes a challenge. At light speed, it would still take over 4 years for a message from Proxima Centauri to reach Earth, meaning any interaction with such a probe would be a one-way conversation conducted across decades. Yet, for all these obstacles, the difference between tens of thousands of years and a few decades cannot be overstated. It's the difference between unreachable and achievable, between myth and mission. The leap from kilometers per second to fractions of light speed is the true threshold of becoming an interstellar civilization. And this is where humanity now stands, at the very beginning of understanding how to make that leap. We've built machines like Voyager and New Horizons that have touched the edge of the solar system. We're designing concepts like breakthrough Starshot that could one day reach the stars. Between these 2 points lies the bridge we must build. The ability to go faster, to harness new forms of energy, and to withstand the dangers of relativistic flight. It's an extraordinary contrast. The Voyagers, still crawling patiently toward eternity at 17 kilometers per second, and the vision of a future probe blazing through interstellar space at 60,000 kilometers per second. One represents where we are, the other, where we're going. And the gulf between them, that gap of speed and time, defines the challenge of our age. But if history has shown us anything, it's that every great leap begins with slow, deliberate steps. The first flight at 20% of light speed might not happen in our lifetime, or it might. The pace of innovation has a way of accelerating faster than we expect, and when it does happen, the universe itself will open up before us, no longer a distant dream, but a reachable destination. Still, even with the promise of near-light travel, enormous technical and physical barriers remain. Building and powering a spacecraft capable of sustaining such speeds isn't simply a matter of design. It's a test of endurance, materials, and ingenuity on a level we've never faced before. The faster we go, the more we must contend with the brutal realities of energy, navigation, and survival in deep space. Those are the engineering limits, and confronting them is the next challenge on humanity's long road to the stars. The dream of traveling at a significant fraction of the speed of light, 5%, 10%, or even 20%, is one of humanity's most breathtaking scientific ambitions. But it's also one of the most brutally unforgiving challenges we've ever faced. Space, at those speeds, ceases to be the serene, empty void we often imagine, and instead becomes a lethal minefield of radiation, dust, and energy. Every problem of modern rocketry, propulsion, navigation, communication, and protection becomes magnified 1,000-fold. And the very physics that make relativistic travel possible also conspire against it. To understand why building and powering such a spacecraft is so hard, it's important to grasp the sheer amount of energy required to move at those speeds. The faster an object goes, the more its kinetic energy increases, not linearly, but exponentially. To double a spacecraft's speed, you must quadruple its energy. To reach even 1% of light speed, a spacecraft the mass of a small car would need the energy equivalent of detonating about 50 megatons of TNT, roughly the yield of the largest nuclear bomb ever built. To reach 20% of light speed, as envisioned by breakthrough Starshot, you'd need thousands of times more energy. The energy problem is what limits every form of propulsion we currently possess. Chemical rockets, which have powered every spacecraft to date, are astonishing feats of engineering, but they are extraordinarily inefficient when it comes to interstellar travel. The energy density of chemical fuel simply isn't high enough. For example, if Voyager 1 had to carry enough fuel to accelerate itself to 20% of the speed of light, the required mass of propellant would be greater than the mass of the entire planet Jupiter. Even nuclear propulsion, though vastly more powerful, faces limits. The best theoretical nuclear fusion engines could potentially reach speeds of 10% of light, but only if we could solve the colossal challenges of controlling and sustaining a fusion reaction in space, managing its heat, and handling the massive radiation it produces. This leads to another problem: shielding and protection. At high speeds, the universe becomes an incredibly hostile place. Interstellar space, though seemingly empty, is filled with gas atoms, dust grains, and cosmic rays, the remains of long-dead stars, and the raw material of new ones. At normal spacecraft speeds, these particles pose little danger. But at relativistic speeds, even a single grain of dust becomes a deadly projectile. A dust particle just a millimeter wide hitting a spacecraft moving at 20%, the speed of light, would release an amount of energy comparable to a hand grenade. Even a single atom of hydrogen colliding with the craft at those speeds would strike with enough force to gradually erode its surface and generate intense heat. the spacecraft would effectively be sandblasted by the interstellar medium, a microscopic storm that could, over time, vaporize unprotected material. For any high-speed probe, this means that shielding is as critical as propulsion. But shielding adds mass, and mass is the enemy of speed. The thicker the armor, the more energy is required to accelerate it, creating a vicious cycle. To overcome this, scientists have proposed clever alternatives. Some suggest building sacrificial shields, layers of lightweight material that would erode over time but protect the vital components beneath. Others propose using magnetic or plasma fields to deflect incoming charged particles, creating an invisible barrier similar to Earth's magnetosphere. For truly small probes, like those envisioned in the breakthrough Starshot concept, the plan is simply to minimize exposure, make the spacecraft so tiny, so lightweight, and so fast that it spends as little time as possible in the danger zone. In other words, instead of resisting the environment, the craft would effectively outrun it. Then comes the issue of navigation. Traveling to another star at 20% the speed of light isn't like crossing an ocean. It's more like threading a needle from billions of kilometers away, at thousands of times the speed of a rifle bullet. A small miscalculation in trajectory could send a spacecraft millions of kilometers off course, missing its target entirely. In the emptiness of interstellar space, there are no fixed landmarks, no GPS satellites, no second chances. A spacecraft must navigate autonomously, adjusting its position using sensors and gyroscopes capable of extraordinary precision. Even more challenging is course correction. At high speeds, making any change in direction becomes exponentially harder. The faster you go, the more momentum you have, and the more energy is needed to alter your path. For a relativistic probe, even a tiny nudge to correct its aim could require an enormous burst of energy. This means the spacecraft must be programmed to make its course as precise as possible from the very start, relying on tiny, pre-calculated adjustments throughout its journey. And if something goes wrong, there's no way to fix it. The communication delay alone is staggering. Even traveling at light speed, a signal from a spacecraft near Proxima Centauri would take over 4 years to reach Earth. A round-trip exchange, "We've got a problem, and here's how to fix it," would take nearly a decade. For a mission traveling at 20% of light speed, there's no room for real-time correction. Every sensor, every system must function autonomously, surviving decades of exposure to radiation, vacuum, and micrometeoroid impacts without human assistance. Then there's communication itself, sending data home. The farther a spacecraft travels, the weaker its signal becomes. By the time Voyager 1's faint radio signal reaches Earth, it has spread out so much that it's weaker than the background noise of the universe. Our most powerful antennas, the Deep Space Network, can barely detect it. Now imagine a probe 4 light-years away, transmitting data from the next star. The signal would be unimaginably faint, perhaps only a few photons per second. Engineers are exploring ways to overcome this, such as using laser communications instead of radio, focusing light beams precisely toward Earth. But even then, maintaining accuracy over such vast distances is an almost impossible feat. And finally, there's the problem of time itself, not just in the literal sense, but in the mechanical and human one. How do you build a spacecraft that will survive for decades or centuries without maintenance? Materials degrade, electronics wear out, cosmic radiation gradually damages circuits and memory systems. Every component must be built to last far longer than any current technology has ever endured. It's one thing to design a spacecraft to last 10 or 20 years. It's another to make one that can function flawlessly for hundreds of years in an environment colder, emptier, and harsher than any lab can simulate. These engineering limits, energy, shielding, navigation, communication, and longevity, form the nearly unscalable wall between where we are and where we want to go. And yet, none of them are impossible. They are merely colossal challenges, the kind humanity has faced before and slowly overcome. Every technological revolution, from the first rocket to the first moon landing, once seemed unachievable. When we dream of reaching another star, we are really dreaming of mastering these limits, of learning to build machines that can outlast generations, survive the fury of interstellar space, and move faster than anything we've ever imagined. Each problem solved, each new material, power source, or navigational system developed, brings us a step closer to that dream. And while we haven't yet escaped the sun's gravitational pull or reached anywhere near light speed, every mission we launch teaches us more. The Voyagers, still transmitting across the abyss, New Horizons, coasting through the Kuiper Belt, and the proposed Starshot sails, waiting for the push of light, all are stepping stones to the same goal: to become a species that can truly leave home and explore the stars. But before we can leave home completely, we must understand that not all boundaries are the same. There's a difference between crossing the heliopause, where the sun's wind ends, and escaping the sun's gravity, where its pull fades forever. This next distinction reveals just how deeply the sun still holds onto everything, even our farthest, most daring explorers. Crossing the heliopause, as Voyager 1 and Voyager 2 have done, is often described as leaving the solar system. It sounds definitive, almost triumphant, as though we've finally broken free from our sun's grasp and stepped into the galaxy beyond. But the truth is more nuanced. While crossing the heliopause means venturing beyond the sun's influence in terms of charged particles and magnetic fields, it doesn't mean we've escaped the sun's gravity. Those two frontiers, the heliopause and true gravitational escape, are profoundly different. The first marks the end of the sun's energy reach, while the second marks the end of its gravitational dominion. To understand this distinction, imagine the sun not as a glowing sphere in the sky, but as a massive anchor in the center of a vast cosmic sea. The heliopause is where the solar wind, that constant stream of charged particles flowing outward from the sun, finally loses its strength, beaten back by the interstellar medium, the thin gas and dust that fill the galaxy. Inside the heliopause, the sun's magnetic field dominates. Its solar wind shapes the environment, carving out the enormous bubble we call the heliosphere. Beyond that boundary, the influence of other stars and the interstellar plasma takes over. It's a transition not of gravity, but of pressure and plasma physics. When Voyager 1 crossed the heliopause in August 2012, it entered this interstellar medium for the first time. Instruments on board detected a dramatic drop in solar particles and a corresponding rise in galactic cosmic rays, a clear sign that it had left the sun's magnetic bubble. But gravitationally speaking, the sun's pull still extends far, far beyond that point. Gravity, unlike light or the solar wind, never truly stops. It weakens with distance, yes, but it never vanishes entirely. Even in the cold emptiness between the stars, the sun's gravitational hand continues to stretch outward, subtly influencing the paths of comets, asteroids, and even our departing spacecraft. In fact, the sun's gravitational influence defines an enormous sphere known as the Hill sphere, the region around a star where its gravity dominates over the pull of neighboring stars. For our sun, this region extends roughly 1 to 2 light-years from its center, nearly a quarter of the distance to the nearest star, Proxima Centauri. That's about 10 trillion to 20 trillion kilometers, hundreds of times farther than where Voyager 1 currently travels. So even though Voyager 1 is over 24 billion kilometers from Earth, it's still deep inside the Sun's gravitational territory. If the spacecraft was somehow stopped, its momentum reduced to zero, it would begin to fall back toward the Sun, pulled home by the faint but ever-present force of gravity. This is why, technically speaking, no human-made object has yet escaped the solar system in the full gravitational sense. Voyager 1 and Voyager 2 have crossed the heliopause, yes, but they haven't reached solar escape velocity from their current distances. To truly escape the Sun's gravity, a spacecraft must travel faster than 42 kilometers per second relative to the Sun, a speed known as the solar escape velocity. Voyager 1, racing outward at about 17 kilometers per second, is moving too slowly to ever completely break free. It's fast enough that it will never return, but not fast enough to be beyond the Sun's gravitational tether. It will forever drift within the Sun's dominion, even as it ventures farther into interstellar space. This distinction between leaving the Sun's influence and escaping its gravity underscores just how immense and persistent our star's presence is. The heliopause is a boundary of energy where the solar wind yields to the interstellar wind. It's the edge of the Sun's electromagnetic and plasma control. But gravity plays by different rules. It doesn't fade abruptly at any distance. Instead, it simply becomes weaker and weaker, blending imperceptibly with the gravitational fields of other stars. Somewhere, halfway between our Sun and Proxima Centauri, the Sun's gravity becomes equal to that of its nearest neighbor. That's the true edge of the Sun's realm, the place where our solar system's gravitational reach finally gives way to another star's. And yet, even escape, in this sense, is a kind of illusion. In the larger tapestry of the galaxy, no object ever truly drifts alone. Every star, planet, and probe is part of the Milky Way's gravity, all bound together in a vast, rotating disk of stars orbiting the galactic center. Even if Voyager 1 were somehow moving fast enough to escape the Sun's pull entirely, it would still be trapped in the gravitational well of the Milky Way. And even the galaxy itself is bound within clusters and superclusters, woven into the cosmic web that holds the universe together. The concept of escape becomes almost philosophical, a reminder that everything in the cosmos is, in some way, connected. For Voyager 1 and 2, this means their journeys are not about escaping at all, but about transcending boundaries, crossing from one domain of influence into another. The heliopause is one such threshold, the border between the Sun's space and the galaxy's space. Beyond it, the Voyagers have entered a region that belongs not to our star, but to the stars beyond. They are, in a very real sense, interstellar travelers, though still faintly tethered to their birthplace. The distinction also reminds us just how far humanity still has to go. To reach the edge of the Sun's gravitational influence, the place where another star's gravity takes over, would require traveling tens of thousands of times farther than we've gone so far. Even at Voyager's speed, that would take tens of thousands of years. We are, in cosmic terms, still standing on the threshold, our first explorers barely outside the front gate. And yet, even that first step is monumental. For the first time, human-built machines have entered interstellar space, sending back data from beyond the Sun's magnetic frontier. They have gone farther than any living thing from Earth ever will for centuries to come. In every sense that matters, symbolic, scientific, and spiritual, they have left home. Still, as we ponder these distances and distinctions, we can't help but wonder what comes next. The heliopause is no longer the final frontier. The next great challenge is to push farther, not just to cross boundaries, but to explore and understand what lies beyond them. That's where the future of deep space exploration begins. The next generation of missions designed to follow the Voyager's path and go even farther into the galactic dark, to study the interstellar medium, and perhaps one day to reach another star. In the wake of the Voyager's success, NASA and the global scientific community have turned their eyes toward what comes next. The next leap outward, beyond the known boundaries of the heliosphere. Humanity's first emissaries have shown us the way, but they were never designed to study the interstellar frontier in detail. Their instruments are aging, their power supplies fading, and their data limited. The next generation of explorers will be purpose-built for the task, to go beyond the heliopause, into the true unknown, and map the outermost edges of our sun's influence. One of the most promising concepts is NASA's proposed Interstellar probe, a mission currently being studied by the Johns Hopkins Applied Physics Laboratory. Its goal is ambitious but clear: to send a dedicated spacecraft to the interstellar medium, traveling 10 times farther than Voyager 1 has so far. If approved, it could become the farthest-reaching scientific mission ever attempted, venturing 1,000 astronomical units from the Sun, that's nearly 150 billion kilometers, over the course of about 50 years. Unlike Voyager, which piggybacked on a planetary exploration mission, the Interstellar probe would be designed specifically for deep space science. It would carry modern instruments to measure the density, temperature, and composition of the interstellar plasma, the faint, charged gas that fills the galaxy. It would also study the shape and dynamics of the heliosphere, helping scientists understand how the Sun interacts with the interstellar environment. These measurements could reveal how stellar winds from other stars behave, and how our solar system's bubble compares to those around neighboring suns. To reach such distances, the spacecraft would need unprecedented speed. Engineers envision using advanced propulsion systems, possibly a combination of solar sail technology and gravity assists from Jupiter, to accelerate the probe to over 7 astronomical units per year, about 33 kilometers per second relative to the Sun. That's nearly twice as fast as Voyager 1. Such speed would allow the craft to reach the heliopause in just 15 years, a journey that took Voyager more than 3 decades. The Interstellar probe isn't just about raw distance, it's also about perspective. From its vantage point, hundreds of astronomical units away, it could look back and study the solar system as a whole, something no probe has ever done. It could measure the faint glow of the Sun's outermost atmosphere, the Helios heath, and even capture views of the planets from a distance so great that they would appear as tiny specks, echoes of Carl Sagan's pale blue dot, but seen from even farther out. Beyond NASA's proposal, other organizations and nations are exploring similar ambitions. The European Space Agency has expressed interest in cooperative missions, while private initiatives are examining ways to miniaturize deep space probes using breakthroughs in microelectronics and propulsion. Concepts like fusion-powered engines, electric sails, and laser propulsion, once confined to theory, are being seriously studied as potential methods for reaching interstellar space faster and more efficiently. These missions would not just expand our reach, they would transform our understanding of space itself. The interstellar medium is the birthplace of stars, planets, and life. By studying it directly, we could learn how our own solar system formed and how others might be born. It's not just about going farther. It's about uncovering the conditions that make existence possible. If launched within the next few decades, an interstellar probe could reach its scientific goals within the 21st century, potentially within the lifetimes of people alive today. It would represent humanity's next great statement to the cosmos, that our curiosity knows no boundaries, and our desire to understand the universe will always push us farther from home. The future of deep space exploration isn't about leaving the sun behind. It's about understanding the sun's place in the galaxy. The Voyagers were our first whisper into the interstellar void. The next probe will be our first true conversation with it. Voyager 1's signal, now faint and fragile after traveling for nearly half a century, is more than just data. It's the first true message in a bottle cast into the cosmic ocean. Every transmission that reaches Earth from that tiny spacecraft has crossed more than 24 billion kilometers of emptiness, weakened until it's fainter than the background noise of the universe. And yet, it still arrives. The Deep Space Network, a series of massive radio antennas spread across the globe, listens for those whispers, piecing together information bit by bit. Each signal is a reminder that a fragment of humanity is out there, still speaking, still exploring. Voyager 1 is humanity's farthest ambassador, a lone emissary carrying our curiosity into the interstellar dark. On board is the Golden Record, a time capsule of sound, music, and images designed to represent life on Earth. It carries greetings in 55 languages, the laughter of children, the sound of rain, and the heartbeat of a mother. It even includes directions, engraved in symbolic diagrams, showing where our planet lies in relation to the pulsars that map the galaxy. It's our introduction to anyone, or anything, that might someday find it, millions or even billions of years from now. The poignancy of Voyager's mission lies not just in where it's going, but in what it represents. It was built by hands that will never touch it again, launched by people who will never see where it goes. And yet, it continues onward, powered by fading nuclear batteries, guided by code written in the 1970s, and still sending signals across the abyss. That persistence makes it one of humanity's greatest achievements, a machine that has outlived generations, carrying our story farther than any of us will ever go. In many ways, Voyager 1 is a reflection of ourselves, small, fragile, and finite, yet capable of reaching beyond our limitations. Its golden record isn't just a greeting, it's a statement of existence. We were here, we reached out, we cared to know. That faint transmission, barely detectable after more than 20 hours of travel at the speed of light, is the echo of our species' first step into eternity. When we step back and take in the full picture, the vastness of space, the sheer scale of the cosmos, everything we've done as a species might seem impossibly small. Even our fastest ships, like Voyager 1, racing through the dark at 17 kilometers per second, move like drifting dust motes against the backdrop of the galaxy. The distances between stars are so immense that words like billions and trillions start to lose their meaning. At this scale, our progress feels like the slow crawl of eternity itself. And yet, that's what makes our achievements so extraordinary. Despite our limits, the fragility of our machines, the finiteness of our lives, the immensity of the distances, we've still managed to send a piece of ourselves beyond the reach of the sun. We've touched the edge of interstellar space. Our signals have crossed billions of kilometers, and our probes continue to move farther each day, carrying the curiosity and creativity that define what it means to be human. The cosmos humbles us with its enormity, but it also magnifies our spirit. It reminds us that, in a universe where stars burn for billions of years and galaxies span hundreds of thousands of light years, we still dared to begin. We built fragile, human-made instruments and sent them into the dark, trusting that their faint voices would one day tell us something new, not just about the stars, but about ourselves. When future generations look back, they'll see Voyager 1 not as an end, but as a beginning, the moment humanity took its first real step beyond home. The spacecraft may be small, its journey slow, but its message is vast, that we are explorers, and we always will be. In the infinite silence between the stars, Voyager 1 continues to drift, still whispering across the void. Its signal grows fainter with each passing year, but what it carries, the proof that we reached out, will endure long after the last word fades. Because in the grander sense, we've already begun our journey to the stars. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.